Okay, so now to prove, okay, let's try to prove the power rule. If it's okay, so let me add a page here. Let me come back to this page a little bit later. The power rule is saying this: if f of x is equal to x to the nth power, then f prime of x must be n times the x to the n minus 1 power. Okay, so this is the power rule. Okay, and then we're trying to prove this. We're trying to make sense of it using the definition of the derivative and using some other mathematical concepts that we know from the past. Okay, we're trying to make sense out of this. Why does this formula work? Why does this shortcut work? Okay, so before getting to that, okay, you do need to know, okay, before proving the power rule, let's think about what it means to have x plus h to the first power. And that doesn't affect, okay, in fact, let's start with 0 power, okay, exponent first. X plus h to the 0th power would just be 1, and x plus h to the first power would be 1x plus 1h, doesn't change anything, what you started with. And then x plus h to the second power requires you to FOIL, multiply x plus h by x plus h. In turn, you're going to get x squared plus 2hx plus h squared, and then x plus h to the third power becomes x to the third power plus, I'll give you the answer for this one. You can multiply it out if you want to, x plus h times x plus h times x plus h. But in the end, this is what you're going to have. You're going to have x to the third power plus 3x squared h plus 3xh squared plus h to the third power. And x plus h to the raised to the fourth power becomes, off the top of my head, it becomes x to the fourth power plus 4x to the third power h plus 6x squared h squared plus 4xh to the third power plus x to the, oh, I should say h to the fourth power. Let me rewrite that h to the fourth power right there. But I want you to notice something here. Okay, so how do I know, okay, how many terms are going to be there for each expansion? Okay, whether I'm expanding x plus h raised to the third power or x plus h raised to the fifth power, that you could probably see it. Okay, if you, for the 0 exponent, you have one term. For one exponent, exponent 1, you have two terms. It appears that the number of terms is always one more than the exponent that you're expanding, that you're using to expand the original binomial. And another pattern that I want you to see is that the powers of the x, the degrees of the x's are descending. X to the fourth power, x to the third power, x to the second power, x to the first power, while the exponents for the h are in the ascending order, meaning that they're increasing by 1. H to the 0 power, which you don't see because it's only 1, h to the first power, h to the second power, h to the third power, h to the fourth power. Okay, this is an example that illustrates the pattern for the binomial distribution. One more thing that I have forgot to mention, I should mention this. How do I know what's, so besides the ascending order and the descending order, okay, ascending exponents, descending exponents, how do I know what the coefficients are going to be? Whether that's 1 or 1, 1, or 1, 2, 1, or 1, 3, 3, 1, or 1, 4, 6, 4, 1. I was able to recall this off the top of my head because for 1, okay, these are the numbers from the Pascal's triangle, which could be a whole nother lesson, or these could be found also by using the idea of combinations. Okay, combination, you have 0 items choosing 0. Okay, 0 C0, okay, 1 C0, 1 C1, 2 C0, 2 C0, 2 C1, 2 C2. Here's another representation of the Pascal's triangle, 3 C0, 3 C1, 3 C2, 3 C3. So this is a review of these many different topics. You have the binomial expansion pattern, you have the Pascal's triangle, you have the concept of combinations. So using all this, can I generalize x plus h raised to the nth power? Can I? Okay, is there a way for me to generalize x plus h to the 1th power? Well, it appears that your leading coefficient for the first term, okay, I'm still expanding x plus h, but I'm raising to the nth power. So that has to do with the leading coefficient is still 1. Okay, just like here, and just like here. Okay, that appears to occur no matter what the exponent value is. So you'll start with 1 times the x to d, but the first exponent of x appears to be matching the actual exponent that we're using for that binomial expansion. So it's 1x to the nth power plus, and the next number could be found by using the idea of combination. Okay, so you could write, so this one represents NC0 for this one. So next one could be NC1. Okay, you have the combination for n number of items chosen one at a time. So NC1 times whatever that number is, but you're going to multiply the number by x to the n minus 1 because your exponents for the x's are in the descending order, while the exponents for the h are in the ascending order. So your second term will be c, the combination, okay, so n choose 1, multiply by x to the n minus 1 times h to the first power, and so on. You could repeat this pattern. Next one you could probably guess to be nc2 times x to the n minus 2 power times the h to the second power, and then plus all the way to the last term. In the last term, you're going to get 1 again, okay? It will be NCN. So you will get 1 again, but then you will gonna end up with h to the nth power as your last one. Okay, so bear with me here. Okay, so we're gonna come back to this pattern, this little mini formula that we made here. Okay, x plus h to the nth power in general form would be 1x to the nth power plus all of these things. Okay, so come back to that idea. So now let's go to this. Okay, so now we want to figure out what the derivative of this would be by using the definition of the derivative. So you could say that f prime of x is equal to the limits as h approaches 0 of f of x plus h minus f of x all over h. In this case, f of x plus h would simply be x plus h raised to the nth power, and then f of x would just be an x to the x raised to the nth power divided by h, and we're still evaluating the limit of this to find the derivative as the h value approaches 0. Okay, we're looking for that tangent. Okay, we're looking for the point at which those 2 points for the secant line converges to make a tangent line. So we got this, and guess what? Okay, so I could rewrite this part using the previous page, the formula that we found, which was all this. Let me cut and paste this right here. Copy, paste right there. Okay, so that becomes that right there. X plus h to the nth power is all of this. Then I have, okay, so all of this minus x to the nth power all over h. And we're still finding the limit of this as the h goes to, h approaches 0. Okay, now notice the first term, 1x to the nth power, cancels out with the term that's outside of it, the term that you're subtracting from that parentheses, x to the nth power minus x to the nth power, that will cancel out. And then notice every term has an h. Do you see that every term has an h right there? Beyond the second term, starting from the second term, every term has an h at least, h to the first power. So you could cancel that h out. You could factor out that h and then cancel out. You could simplify with the h on the denominator. So what ends up happening is you get this. So you still have NC1 times dx to the n minus 1 power yeah, the h canceled out with that. So okay, plus nc2 times x to the n minus 2 power times the h plus dot 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 plus h to the in the end, now instead of having an h to the nth power, that will be h to the n minus 1 power, because you're dividing h to the nth power, you're dividing that by another h on the bottom. So what's the point of all this? Okay, now at this point, okay, so we don't have any more we're not dealing with any kind of fractions. And notice that your h value is approaching 0, but at this point we could substitute 0 for h. So that would make the second term 0, that will make the third term 0, fourth term 0, fifth term 0, and the very last term will be 0 as well, because your h value is 0. So in turn, the only thing that's left after you use substitution to evaluate the limit is nc1 times x to the n minus 1 power. So nc1 times x to the n minus 1 power. And what is the value for nc1? That would be just n. And so you end up with everything. So after evaluating that limit, you end up with n times the x raised to the n minus 1 power. And this is why the derivative of x to the n power, by definition and by using the binomial distribution, is n times x to the n minus 1 power.